Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we're going to be talking in AP Chemistry, talking about solutions, redox reactions, and we're not going to talk about the thermodynamics. We're going to talk about reactions in aqueous solutions. What does it mean that it's aqueous? It's in what? Water, right? Okay, so aqueous solutions, back on draw, we're going to go with red. Is a solution where water is the medium for dissolving, like Kool-Aid. So part of this you will already know from honors, and it's just a review, but part of it's new. So this you should remember, the solute. What is that? What gets dissolved, right? And the solvent, what does the dissolving? Now, so how you remember it is make the V into a little cup and color it blue. It's got the water in it. Solvent is the water. Solute is the Kool-Aid. Now, sometimes you have two liquids. Then which one's the solute and which one's the solvent? The solvent has the most. So say I'm mixing alcohol and water, and I've got more water, it's the solvent. Alcohol is the solute. Okay. Electrolytes and non-electrolytes. When ionic solids dissolve, they become charged ions, sort of redundant, in solution and can conduct what? Electricity. I always want to sing the electricity song from Schoolhouse Rock. So example, salt water. Okay, everybody who had me for honors did a lab where we compared salt water and sugar water. And if you remember, we used a little probe and we stuck it in there and it lit up in the salt water because it's an electrolyte, and it did not in the sugar water. Do you remember that? Okay, so salt water is our electrolyte and non-electrolyte sugar. So an example is Gatorade. We got the Gatorade symbol down there. Okay, so if you exercise real hard and you chug water, what happens sometimes? You throw up, right? You barf. Anybody else ever done that besides me? So I like to run. See my medals over there? I just signed up for the Georgia Aquarium run. Last time I ran it, I beat 1,000 people. I came in 500th. I was number 500. But anyway, I beat 1,000 people, and most of them were younger than me. But anyway, so I just signed up for it again. So I don't usually drink water while I'm in the middle of a run, right? But it seems so luxurious that there's all these people handing you water. And it feels like wrong not to take it. So I was running the Peachtree Road Race, and they were so nice handing me cups of water, and I kept taking the water and drinking it. I barfed all over a Texaco parking lot. Should have just let that water be and ran my race and not be drinking that water. But the reason why is, remember when you learned about in honors biology, you learned about hypertonic, hypotonic, isotonic. Remember that? Osmosis is when you learned it. Okay, so your body is salty. That's why your tears are salty. Your snot is salty. That's why some little kids will sit there and eat their boogers, and your spit is salty. You ever notice that? So if you put all this water in you that's just water, it's not really an electrolyte, and you're all salty too fast, your body needs to make it salty to absorb it. It'll reject it, and you'll barf. And then if you're exercising hard, you're going to get dehydrated, and it can be really dangerous. So University of Florida Gators, they had their football players out there practicing drinking water, barfing. So they decided to make, in the chemistry department, an electrolyte for them to drink, and they made Gatorade. So Gatorade is after Florida Gators aid, and it's salty and sweet. It has a good saltiness. You can chug it when you are exercising, and you will not barf because of the salinity. So, Gatorade. See, when I'm out running, those nice little people with the cups need to be offering me Gatorade, not water. But now I just don't take them. I just run on by. I've learned my lesson. Don't throw up. I felt so sorry for the people who were running by me throwing up. Because, you know, they were already feeling kind of bad. You know, we were on what's called Cardiac Hill, the big hill at the end. And here I am barfing. It did not make them have a pleasant run. So I felt great after that, though. I just sprinted up that hill. I did. All that, it was gone. I felt so much better. Okay. So how compounds dissolve in water. Solvation is the attraction of a solvent with ions of a solute. Dissociation is the separation of an ionic compounds from one another. So if it's an aqueous solution, it's dissolved in water. So how does this happen? Water has partial charges symbolized by the lowercase Greek letter delta. It looks like an 8 that you didn't finish. And it ionizes other compounds. So over here, draw a water molecule. So there's the oxygen. Here are our hydrogens. The hydrogens get partial positive charge, the oxygen negative, because oxygen is a bully and steals the electrons, and the poor little hydrogens don't get them. So there's water over there. So how we draw that is we draw this and we say on this side, water has a partial positive charge. On this side, it has a partial negative charge. So here are our waters, and the oxygens will line up with the positive sodiums. The hydrogens will line up with the negative chlorides. And remember, all of this is vibrating. Molecules are in constant random motion unless they're at absolute zero. And if it's at zero, the water's all frozen. So this is liquid water. Everything's vibrating, and it pulls it apart. That's why I said, because I think this looks a little like Mickey Mouse. My students will say it looks like Kermit the Frog. Either way, it attacks. Yes?
Is that why they say water is polar?
Yes, because it has a positive and a negative end.
Okay, I was trying to figure that out this whole time.
There you go. It's polar. It has poles. It has ends, just like the Earth does. The Earth has the Antarctica and all that. And so we've got the two ends of the water molecule. Non-polar don't have ends like that with charges. Okay, so strong and weak electrolytes. Strong electrolytes are solutes exist completely or nearly as ions. For example, hydrochloric acid breaks into hydrogen and chlorine. Water-soluble ionic compounds are strong electrolytes. So like salt. Salt in water, strong electrolyte. So weak, if you got strong, you gotta have weak. Weak electrolytes or solutes are mostly neutral molecules with only a small fraction as ions. This is not solubility. This is all dissolved, okay? So this is aqueous. So we're not talking about solubility. That's when things dissolved or not. These are dissolved. It's just, do they break apart completely when they dissolve, or are some of them still together? And some of them are still together. It's at equilibrium. You need to draw your arrow both ways. Drawing that second arrow. Word doesn't let me do arrows like that, so we just draw them in. Okay, we feeling good about that? Yes, Atticus.
You said stuff like salt is a strong electrolyte, so would strong electrolytes be stuff that's really good for us to drink, or is that not?
No. Salt water is fine for you to drink. Gatorade is very salty. Dasani water is very salty. Have you ever noticed how salty it is? It's definitely an electrolyte. It's not bad for us or not. It's just weak electrolytes don't dissolve very much. Strong do. This is not dangerous. Good question. Very good. Anything else? Okay, so now the other thing we have is solubility. So this is whether things dissolve or not. There are solubility guidelines for ionic compounds. So there are rules, and I was hoping y'all would get these rules given to you on the AP test, but looking at those papers I gave y'all yesterday, I didn't see any solubility charts. So what that means is they expect you to memorize what I'm about to tell you. That you don't have to memorize every chemical, whether it dissolves or not. All they're going to want you to know is the general trends, and there are certain ways, mnemonic devices to remember them that everybody uses. I did not make these up, okay? They're just like Roy G. Biv didn't make him up. These are ones, so how you know if things dissolve or not. So the first one is NAG-SAG. Now, unlike Roy G. Biv, which sounds like a guy's name, NAG-SAG doesn't really mean anything. So how we're going to remember is this little pig, okay? So you know how horses are sometimes called nags? Now this looks like a nice little pig. He's mean because he is making fun of a horse in the barnyard for having saggy skin. An old horse, and he's going, nag-sag. So everybody get that in your brain. We're going to remember nag-sag. Okay, everybody got it? There's the mean little pig. Okay, it determines if a double replacement and reaction will occur if a precipitant, the abbreviation for precipitant is PPT, forms, then the reaction happens. So everybody, I heard that Miss Corn did it too. In Honors Chem, we did a lab where we took two clear things and we poured them together and it made stuff that looked like yellow paint. Remember that? So that yellow paint is a precipitant, and I let it sit for a day so that it all settled out and you could see that it was really little like yellow dust that settled out. That's a solid precipitant, so that was a double replacement reaction that did happen. If you mix your two, if you got your two beakers and you mix them together and it just makes liquid, then the double replacement reaction doesn't happen. Everything just stays as ions in solution. Nothing gets replaced. Everything's just floating around. And we'll talk about that a little bit more on the next page. Okay. So, I just gave you an activity, green piece of paper. Everybody look at it. This is a more detailed look at NAG-SAG. It's got a little piggy on there to help you remember NAG-SAG. Okay? All right, so when you look at this, how you know if something dissolves or not is up at the top, NAG-SAG is soluble. So NAG-SAG dissolves. This is, so not it doesn't dissolve, these dissolve. So look up at the top. The things that dissolve are nitrates, acetates, group 1, sulfates, ammonium, and group 17. Okay, so now look at the top part where it says that these things dissolve. The first ones they have listed are lithium, sodium, potassium, ammonium. That is group 1. Lithium, sodium, potassium are from group 1. So compounds made out of them dissolve because of the G in NAG. The ammonium is the A in SAG. Everybody following that? So they dissolve, and there are no exceptions. Okay? Got that memorized. The next one is, notice that the nitrates are the next group down. NO3 is nitrates, and C2H3O2 are acetates. And notice that the nitrates is the N in NAG-SAG, and the A is acetates, and they always dissolve. If you see a chemical that would be that, it's going to dissolve. Good so far? Okay. Chlorine, bromine, iodine, those are halogens, and they're mostly soluble, but they have an exception. So now look down at the bottom of the page. The exception is PMS. So I told you I didn't make this up. So this is our other one. PMS for individuals who experience it is a pain. Okay? And having to remember these exceptions are a pain. So that's how we're going to remember. We got mean little pig, NAG-SAG, and now we've got PMS is a pain. Okay, so these are the exceptions. And both the sulfates and group 17 who have exceptions, it's PMS. Okay, so what does that mean? If you look down at the bottom, PMS, they're not soluble sulfates or group 17, and these are the ones, P. Now, this is a little confusing, but you can do it. P stands for lead, because the symbol for lead is PB. Okay, everybody got that in your head? Now, this is where it gets tricky. The M is mercury, and M for mercury, but the symbol for mercury is Hg. Lead starts with an L. But it's got to be PMS so we can remember it's a pain. Okay, everybody getting that in your head? Okay, and then S, once again, is silver, not A for Ag. So P for lead, M for mercury, S for silver. So now go back up and look at up here where it says the halides are mostly soluble. The exception is PMS. Do you see how that's lead, silver, and mercury? Everybody got that? Okay, so now look at the sulfates. They're mostly soluble except for the exception, the second exception, lead, silver, mercury. PMS. Okay, that's our first exception. Now the sulfates have another exception, Castro-Bear. So everybody see my little drawing of Winnie the Pooh. He has become communist. Y'all know who Fidel Castro is? I gave him his little communist hat and beard. If you don't know who Fidel Castro is, you might need to go look him up, but he's our Castro-Bear. We have communist Winnie the Pooh. Don't get on the test and go, communist Winnie the Pooh. What is it? Castro-Bear, okay? So what is Castro-Bear? I told you I didn't make these up. I'm just helping you remember them. So Castro is the exception to the sulfates. It's calcium, Ca, strontium, Stro, and then barium, Bear. Castro-Bear. Okay? Everybody getting Castro-Bear in your head? And that's just for the sulfates. Okay, we got it? Okay, so that is how we know what's soluble or not. Notice the second part. The next ones, they are soluble. They're insoluble. The first ones were soluble. These are insoluble. Carbonates and phosphates, hydroxides, sulfides are mostly insoluble. But you don't have to memorize those if you remember NAGSAG, Castro-Bear, and PMS. Then you'll know what is soluble, and then and the exceptions, and then everything else you can just sort of think is going to be insoluble. Okay, that's how you do it. And then, but you can look over those some more. All right, y'all handled that new knowledge pretty good. I did tell you a little bit about it in honors, but we didn't go into as much detail as we will. Okay, we talked about all that. Okay, our detailed list. So make a little note that you can see in your book, page 127, and also see table 4.1. Okay, so knowing that, will this happen? So this is a hydroxide, and that's a nitrate with sodium. Will this happen? Yes or no? Okay, let's look at our rules. Okay, so nitrates, right there it says, are soluble. So this is not going to make it happen. What we're looking for is a precipitate. So now we're over here at hydroxides. Are hydroxides soluble? Well, they're not part of our NAGSAG. So it's probably that we're going to make a precipitate. Now look right here on your chart. Oh, there they are. Hydroxides, insoluble. So we know that that this is going to happen. So we can draw an arrow down. That's a symbol for a precipitate will form. And will this happen? Yes.
Wait, so both the elements don't need to be soluble.
No, just one.
Just one? Okay.
Just one. If one of them is insoluble, then it becomes a precipitate and it happens.
Okay. But if both of them are soluble,
then it doesn't happen. Everybody, see the fish I drew on there? Everything's just swimming around as ions. No reaction happens.
okay. So there needs to be a precipitate for that.
Yes.
Okay.
That means a reaction happened. Otherwise, everybody's just fish swimming around. That's why the fish is there. That cute little fish. Okay. A little bit more about this. So a double replacement reaction is also called an exchange reaction or metathesis. Boy, that sounds fancy, doesn't it? So you can predict the products, decide if it will happen, balance it, and always remember if you write it, that cations have to be written first. So somebody on the AP Chem teachers Facebook group was saying, would they count off if the student wrote the anion before the cation? And all these teachers said yes. So remember, cations go first. Kitties before fire ants. Okay, so example, here we have silver nitrate and silver chloride. Is this going to happen? Well, first we'll just write it. So the silver goes with the chloride, AgCl, and those are both 1, so I can just write them together. And then the sodium we go with the nitrate. Okay, so, and those are ones too, so I can write it. So how about the nitrate? Is it going to precipitate out or be in solution? Look back at your little things. Nitrates, no exceptions. So this is swimming. How about this silver chloride? Well, now we go look at chloride for the halides. And they, do we see any exception there for chlorides? Yes. What's the exception? Silver. What's our mnemonic device that told us that? PMS. It's the S of PMS. So this precipitates out, and yes, that's going to happen. That's not terrible, is it? Okay. Miss Weeks is here. You're welcome. All right. So let's go on. Ionic equations and spectator ions. This is something else brand new. It's so exciting. Okay, so what we're used to doing is writing equations that are called molecular equations, and that's where you write all the compounds. Everything is compounds or elements. But these are just regular equations that you're used to. Lead nitrate plus potassium iodide makes lead iodine and potassium nitrate. That's the reaction that makes the yellow stuff that looks like paint. There it is, okay? But we can think about that some of these ions are just swimming around like fish. So we can write it, instead of molecules, we can write it as ions. So a complete ionic equation shows all the soluble strong electrolytes as ions swimming around in the aqueous solution. So lead ions, remember remember we started off with just two things that look like water. Everything's swimming. Nitrate swimming, potassium swimming, iodine swimming, and then we pour them together, and this is our yellow paint stuff, our lead iodide. So the potassium is still swimming, and so is the nitrate, okay? Notice there are things on both sides of the arrow that don't do anything. They're just swimming. They're not reacting, okay? So they are called spectator ions, and just like in math, you can cross them out. So over on this side, I've got a K. So over here I've got a K. I can mark those out. Here I've got an NO3 swimming. There I've got NO3 swimming. I can mark those out. And what is left is called the net ionic equation. So I've got lead ion plus the iodine ion makes the compound, the precipitate. Okay? So how do we feel about that? That's a new skill. We haven't done those before. That's fun. I like marking things out in math. So here's an important new concept that's not taught in honors. Charge must be conserved in chemical reactions. So this is a new AP skill that we are not only going to balance equations, we're going to start balancing charges, the electrons. Because remember, the law of conservation, what you put in is what you get out, including electrons. They can't disappear, okay? So the sum of ionic charges must be the same on both sides of a balanced net ionic equation. So here, this is plus 2. There I've got 2 minus 1s. So if I do 2 times -1, that's -2. 2 minus 2 is 0. This has a charge of 0. 2 minus 2 is 0. We good with that idea? I like math when the answer is 0. Yes?
So the charge of the reactants has added to 0?
If you're, yes. I'll just say yes. There's a little more to it, but we'll talk about that in a second. Yes. Yes, because that's how many you have.
How do we know iodine is its charge?
Because it is a halogen in row, right? That row right there, this is a -1. 1, 2, 3, skip, -3, -2, -1, zip. Yes.
I thought that when you were putting elements into a compound like that, ionic bond, don't you balance the charges already?
You do here.
Yeah, like.
But we gotta have it on this side too.
So you just have to write the charges on the On the side.
Yes.
Okay.
And make sure that it all adds up to 0.
Okay.
So this is just introducing something new we're about to do. We're laying the foundation to something new we're about to do. Okay, but we're not there yet. Acids, bases, and neutralization reactions. So let's talk about that. So our acids is our lemons. Our bases is our soap. So I didn't want you to get confused because then I'm going to start talking about acids. Soap is a base, not an acid. So acids ionize in aqueous solution to form hydrogen ions, which are really a proton. Because hydrogen is just a proton and an electron, and if it lost its electron, it's a proton. There it is. So it's also called a proton donor. There are 3 definitions of acids that we're going to learn more about in a later unit. But you already learned a lot about in honors, so that one is one. There's a few units that are AP units that I think y'all pretty much know already. I think y'all are really good with the electron configurations already and the acids and bases. So if we have to cut something, that's the place we could cut. Okay, so there are organic acids, meaning they have carbon in them, and they always have Cu in their formula. Organic acids say Cu, which means a carbon double bonded to an oxygen, single bonded to a OH, and then it can be bonded to something else. So organic acids like aspirin, vinegar, have this in it. Coffee is also a acid. So molecules of different acids donate different numbers of hydrogen ions. For example, hydrochloric versus sulfuric, H2SO4. Hydrochloric can donate 1 proton. Sulfuric can do 2. Notice that acids start with H. So when sulfuric donates 2, it does it in 2 steps. First, 1 H comes off, and then the other H goes off. The first H goes off in one direction, but the second one, it reaches equilibrium, and the arrow goes both ways. It goes back and forth. How do we feel? Doing okay with that idea? Okay. So acids, not that you should be tasting of anything in the lab, taste how? Sour. What do they react with? Metals. That's why I got a metal guitar on here somewhere. And what color do they turn blue litmus? Red. So here you should draw that this, you should color it blue and make the end of it pink as it's being dipped in the acid. Also, I just forgot this when I was typing. pH is equal to 0 to 6.9. So there's your acids. Now bases accept or react with a hydrogen ion. So they're from things like hydroxide, OH. They introduce hydroxide ions into the water. That's OH's hydroxide ion. You need to memorize that. So for example, we got water plus ammonia makes hydroxide ions in the ammonium ion. So ammonia is a weak electrolyte. So how do they taste? Bitter, and not bitter like coffee. It's bitter like soap. How do they feel? How does soap feel? Slippery. Eyes not showing up. They react with what? You remember this? Fat. Yes, it's how soap's made actually. And it turns red litmus what color? Blue. And the pH is 7.1 to 14.
I have a question.
Yes.
What is litmus?
It's just a chemical that reacts. Remember in our lab that there's a lot of chemicals that react to pH, including tea. So when you add lemon to tea, it gets lighter. It's because it's an indicator. Red cabbage juice, do you remember that one? Like the red cabbage that's in your salad, if you boil it down and get its juice, it acts just like other indicators, turning a rainbow of colors between acids and bases. So there's a lot of natural indicators. You can Google it, and there's like lots of them. Like blueberry is one. A lot of fruits and vegetables are natural indicators. Okay, strong and weak acids and bases dissociate completely in water. Okay, they are strong electrolytes. Let's see. strong acids are more reactive than weak acids. However, only if it depends on just concentration of the hydrogen ion, because some other factors like hydrofluoric is a weak acid, but super reactive because fluorine is really reactive. So there's a table in your book, and I think you need to memorize what is a strong acid. So look on page 132, there's a list of like 7 strong acids that you need to memorize, and then if it's not one of those, you could just assume it's weak. Oh, I meant to tell y'all. Okay, so I've had a request from Carlos to not bring your books to school every day. So I figured out this can be done. You can leave this could be your home book. And I've got enough books in Miss Foster's book room where I can take out all the honors chem books and move them down to where physical science is. And I can have a copy of your book in here for you to use in case you need it. And then put it back. Just don't take my extra books here, okay? That'll be nice, won't it? Because this book's heavy. It's not that thick, but it's really dense for some reason. Okay, so you need to look at those. Okay, so how can you decide if something is a strong acid or a weak acid? You can see sample problem 4.5. It talks. You can look at it and you can see where they have disassociated completely, which was HY would be strong. So if you got your book open, look at that little thing. Let's see. So that is greater than HZ is weak, not very disassociated, and HX is even weaker, even less disassociated. What they would expect you to do is just count how many of them are stuck together and how many of them have come apart. Okay, so how can you tell if an acid or base is weak or strong in the lab with an indicator? Like that cabbage juice or litmus paper. Well, not litmus paper. It's just going to say acid or base. But universal indicator. You can also do it with a meter, a pH meter. So universal phenolphthalein, hydroion papers, indicators are going to let you know about acids and bases. So how do we identify strong and weak electrolytes? So this might be something you have to do. Ask yourself, is it ionic or molecular? Ionic or covalent? If it's ionic, it's a strong electrolyte. Boom. If it's covalent or molecular, is it an acid or a base? If it's an acid, is it one of the 7 strong acids you are memorizing out of table 4.2? If it's so, it's a strong electrolyte. If it's not listed, it's probably weak. Number 3, if it's a base, use table 4.2 to see if it's weak or strong. So there's a list of strong bases. I think there's 8 of them. I think you should memorize them. If not, they're weak. Everything else is probably a non-electrolyte.